Hi everyone! In this video we are going to explore more deeply the intermolecular forces involving ions, and specifically the ion-ion interaction and the ion-dipole interaction. Now the ion-ion interaction is the strongest interaction between particles, and this is because of the strong electrostatic attractive forces between the two ions. A basic requirement for the ion-ion interaction is that we have a cation and an anion. And we've already seen this type of interaction in our ionic compounds that we looked at back in chapter 6. So the force between the ions is going to be directly related to the electrostatic potential energy associated with those two ions. And we know from Coulomb's law that for two charged particles, the electrostatic potential energy is proportional to the two charges divided by the distance those ions are separated. So if we have a positive and a negative charge, and they are separated by some distance d, the electrostatic potential energy can be approximated by the charges divided by the distance. So when we look at specific examples, let's say we look at NaCl versus magnesium oxide. The tiebreaker here is going to be the charge, right? We have +1 and -1 in NaCl, and +2 and -2 in magnesium oxide. So the electrostatic potential energy for magnesium oxide is going to be about 4 times more negative, more favorable. The force is going to be 4 times as much. Not to mention that the ions are smaller, so then the distance is smaller, which is also attributing to an even lower electrostatic potential energy. But how this plays out in a practical application is in melting point, its physical properties. So the stronger that attractive force is between the ions, as predicted by Coulomb's law, the more energy in the form of heat, so the higher temperature that will melt at. So when we're considering trends in melting point for ionic compounds, we need to think about this ion-ion interaction and how strong it is. The number one thing to consider is the charge, right? The charge appears in the numerator here. It's going to have a multiplicative effect on the electrostatic potential energy and therefore the forces at work holding those ions close to one another. And remember, they're solids, right? Those ions are just jostling in place, and we need to put in enough energy such that they can move freely past one another and slide past one another. That takes energy. We have to heat it up to reach the melting point. So magnesium oxide, +2 and -2, will have an overall stronger attractive force, will have a higher melting point than sodium chloride. When we're looking at examples within the same charge family, so let's look at NaCl versus NaBr versus NaI. The charges are all + and -1 in these examples. So we need to move on to the other criteria, which is the distance those ions are separated. And this is going to relate back to the periodic trend in ion size. So as we move down a group, ions are going to increase in size. And the larger those ions are, the larger this distance is. Distance in the denominator being large would cause this term to be overall small. So ions that are separated by a larger distance will have a smaller electrostatic potential energy, a smaller force holding them together. Their melting points will be lower. And we can see that from the data presented here. Why don't you try thinking about the charge and distance and rank these compounds according to their melting points. When we are evaluating a series of ionic compounds to determine their melting point, we need to first look at the charge. So in the aluminum nitride example, we have +3 and -3 ions. In barium sulfide, we have +2 and -2. In NaCl, +1, -1. In rubidium iodide, that's also +1 and -1. Remember, we can recognize the charge on these based on the position of the periodic table, knowing how many electrons a metal ion prefers to lose. So based on the charge here, we can rank that aluminum nitride would be the highest melting point because it is the largest charge. So according to Coulomb's law, we would have the most negative electrostatic potential energy that would cost the most energy to separate those ions. Then we would go to barium sulfide. This would be next. And then we have a tie between NaCl and rubidium iodide. So we break this tie by looking at the distance that these ions are separated. And we don't need to know the actual distance for this. We just need to know the trend in ion size, right? As we move down a group, ion size increases. So the fact that rubidium is below sodium in group 1 and iodine is below chlorine in group 7, both rubidium and iodide will be larger than sodium and chloride. So rubidium iodide will have a large distance, a less negative electrostatic potential energy. It will have the lowest melting point. So we actually have these arranged in order from lowest to highest as written here. And we, again, first consider charge, and then as a secondary factor to break any ties, look at the distance that these are separated by. Ion-ion interactions exist beyond those in our solid ionic salts. They are common in living systems, for example. We have charges such as ammonium cations and phosphate anions that are responsible for holding proteins to DNA. So the backbone of DNA is charged with these phosphate ions, and then the proteins often have charged amino acid residues that can interact through this ion-ion interaction. And this, like we talked about, is a very strong force and works to keep these molecules aggregated together. When considering the ion-dipole interaction, our formula is going to look a little bit different. The energy involved with the interactions between an ion, which is charged, and a dipole, which is not formally charged, is related to the charge of the ion and the dipole moment of the polar molecule, and divided by the distance squared. Now, these types of forces are very sensitive to the distance, so more sensitive to distance than our ion-ion interaction, which is why we see this raised to some power. So that's going to increase the effective distance on the electrostatic potential energy. Now, I don't expect you to be able to remember all of these formula for the various types of intermolecular forces that we're going to study, but you do need to keep in mind just generally that, for example, the ion-dipole interaction depends on the charge of the ion and the dipole moment and the distance. So don't get too bogged down in the details of the formula. The most typical example of the ion-dipole interaction is when we take an ionic compound or a salt and dissolve it in water. So water is polar, it will have a dipole moment. The charges will dissociate and form these ion-dipole interactions with the solvent. And here are some examples. We get these solvation spheres of polar molecules surrounding the ion, and they orient themselves in a way that the appropriate dipole is attracted to that ion. So the positive ion, for example, will attract the negative end of the dipole, and the negative ion will attract the positive end of the dipole. These interactions will be explored in more detail when we talk about dissolution, the process of dissolving. Another example of the ion-dipole interaction can be found in living systems, and this is just one example of many. So we have these charges on those amino acids in the form of the NH3+ cations. They can interact favorably through an ion-dipole interaction with the negative end of a polar bond. So the carbon-oxygen double bond is polar with a negative dipole on the oxygen, and carbon-nitrogen bonds are polar with a negative end towards nitrogen. So the ion can coordinate with these groups in some structures in DNA, and this is also a favorable electrostatic interaction that holds these components together. I hope you enjoyed the video, and thank you for watching.